Everybody has heard of Burning Man, I suppose. So you know how you know someone was at Burning Man? They're going to tell you. So incidentally, I was at Burning Man, and this is what it looks like when you go out of Burning Man. This is like a huge traffic jam. They call it Exodus. I was stuck there for about 8 hours. I was one of the lucky ones. My friends waited 12 hours in that line, in that queue. It's kind of fun, actually. It's not too bad. But here's the deal. We're going to do a little bit of engineering on this problem. So this is basically how it looks like. There's one lane that's going out of the desert. It's going to Reno, or actually Gerlach, but same. And the speed limit on that lane is 55 miles per hour, which for the European people in the audience is about 90 kilometers per hour. And what they did was, as you saw in the previous picture, is they opened up about 10 lanes in the desert. They marked it. It's like a highway. And when you open 10 lanes that all merge into one lane, what you get is basically 0 miles per hour. Okay, so everyone's basically standing still, and everyone's again like moving a little bit, stopping again, moving a little bit, and yeah, that's the way it's been working for years. Now, this is very, very inefficient. Okay, why is it inefficient? A few reasons. First of all, everyone is stuck in the desert, and the cars break down, and they have to basically get people out of the way. You see like tow trucks and stuff like this. It's a huge waste of fuel. People actually waste all their fuels just waiting, and then they have to bring tankers in and resupply them. So it's very, very problematic and very inefficient. But the worst thing is that actually the speed, one of the reasons why it's very low is because if you think about it, when you move and the car behind you has to move, the way it works is I move a little bit, then it takes a while before the other car starts, moves a little bit, the car before it does the same, so on, so on, so on. And there is actually a mathematical model for traffic, which is called traffic flow theory. And what they call this kind of behavior is traffic flow instability. So one of the things that they found out was that actually, if you think about a highway, once you have traffic flow instabilities, throughput becomes lower. Okay? So we're going to try to optimize this. And here's the solution I came up with. And remember, I had 8 hours to analyze this problem. So basically, the idea is you put one lane all the way. Okay? And what happens when you do this is you have flow. And the speed on this one lane should be, in theory at least, 55 miles per hour all through, and you're not going to have any traffic flow instabilities. And if you don't have any traffic flow instabilities, then your throughput will be optimal. Now, of course, this is not the way it's going to work in practice because some cars are going to break down, so probably the best solution would be 2 lanes instead of one, going around 20, 25 miles per hour. And if the car breaks down in one of them, then you still have the other one for redundancy. Okay? So this is an example of how you can use mathematics to optimize a seemingly pretty easy problem. But the interesting thing about this problem is that the answer that you come up with intuitively is wrong. And only after you do the math, you analyze it properly, and you model it, you find out that this intuitive solution was wrong. And if you look it up online, you will find that this result, that adding lanes or adding roads actually slows down traffic, is something that today is well known. And of course, politicians have never heard of it, so they keep building roads. But every traffic engineer nowadays knows that if you add roads, traffic will become slower. Okay? So this is one of the reasons why I'm talking about mathematics here today. Because when you talk to engineers about mathematics, this is the kind of answer, and this is the kind of reaction you get. People are afraid of mathematics. And we shouldn't be afraid of mathematics. Mathematics is not that scary, and it's not that difficult. And it's not about numbers, it's not about formulas. What mathematics is about, it's about modeling, it's about making your assumptions explicit, and using logic to work with them. And of course, it allows you to use pre-existing models that other people have researched and thought about to get insights on the problems that you have. So today, we're going to talk about the mathematics of scalability. First of all, because I'm interested in scalability like most of you, but also because it's a good example of how we can use mathematics to our benefit. But before we talk about scalability, remember mathematics is all about making your definitions and assumptions explicit. We need to define what scalability is. So anyone wants to contribute to this? Like, what is scalability? Define scalability. Anyone? Anyone? The ability to grow up. The what? Okay. More output with less input. Okay, cool. So I just want to comment that for a room full of people dealing with scaling systems, we're not getting a lot of responses here. But this is my version. It's like a more, let's say, explicit definition. It's a relation between resources, processing time, and problem size, or the amount of work that needs to be done. Okay? You can say that this relation is S for scalability, and R would be resources, T would be time to process the problem, and W would be work. So we differentiate between two types of systems, a batch system and an interactive system, where the difference is that for the batch system, the amount of work to be done is constant. And basically, what we do when we scale is we add more resources, and presumably the time for completion will be less. And for interactive systems, like the kind of web systems that we have, then the time for completion is constant. We're talking about X per second, X per minute, whatever. So we're talking about constant time slices. And the amount of work to be done, or the throughput, the amount of work that is being done, scalability is a relation between that and the amount of resources that we have in the system. So we can put that on a chart and ask ourselves what kind of behavior do we get in our scalability. So if everything is perfect, then what we would get is what is known as linear scalability. We add more resources, we get like a proportional increase in our output or in our throughput. This is not the only behavior that exists. So if you ask, for example, VCs, people who invest, they say that scalability is super linear. You add more resources, and for every extra resource, you get even larger increase. Okay, but yeah, we're not VCs. We don't think the world behaves like this. If you ask engineers, they would tell you this is the type of behavior you get in scalability. You add more resources, but you have diminishing returns. For every resource you add, may be a server, might be an engineer, doesn't matter, you get less work done. Okay? Until eventually you can add more, but you don't actually get any benefit. But in reality, in most cases, this is how it works. Okay? After a certain point, a certain maximum point, you start getting reduced performance for the system. Okay, so you add more resources, but actually your throughput is getting lower and lower and lower. And we're going to talk about why this happens in a bit. Okay, but just remember this. This is known as retrograde scaling. So we had linear scaling, we had superlinear scaling, sublinear scaling, and retrograde scaling. Now, when we're talking about scalability, we need to talk about statistics. Why? Because when we're dealing with systems that have a lot of parts, or a lot of transactions, a lot of things happening, the way we reason about those things mathematically is two fields, actually, statistics and probability. They're kind of related to each other. I'm not going to go into the differences. But right now, we're just going to say statistics, but actually what we mean is probability and statistics. So I'm going to give you a very, very quick explanation of everything you know about statistics in 5 minutes, okay? This is it. Someone will win the lottery, but it's not going to be you. Okay, so let me explain. Let's say that you have a lottery. Everyone has lottery in the countries. And what are the chances of someone, anyone, not someone specific, winning the lottery? They're pretty high. Okay? Most weeks, someone wins the lottery. If no one wins the lottery, we're going to keep the lottery running until eventually someone wins. Okay? So the probability of someone winning the lottery, about 100%, about 1. Okay? What are the chances of it being someone specific, namely you? Not high, right? It's about 0. So this is the difference between basically a statistical aggregate or a statistical event that doesn't have to be definite and something that has to be definite, and the chances for that are pretty slim. Okay, so that's basically how statistics work. What is behind this is something known as the law of truly large numbers. Okay, so what is the law of truly large numbers? If you have a system where there's a lot of events happening, a lot of things happening, and a lot of paths, let's say a country like China, where you have 1.5 billion people, okay? Everything that's real will happen eventually. Why? Because you have a lot of chances, a lot of lotteries running. So if you think about the lottery, we've been running the lottery for decades. Like I think in some countries more than 100 years. And during that time, a lot of weird things happened in the lottery. We had the same numbers coming up over and over again. We have people winning the lottery twice or even 3 times. And we had the same numbers popping up sometimes a week after another week. We had the same numbers popping in different lotteries. We had people with tickets to 2 different lotteries where the winning numbers of that lottery was on that ticket and the winning numbers for the other lottery was on that ticket. We had crazy things happening, and every time this happens, people suspect there was foul play, but there wasn't. It's just that rare things happen all the time if you have enough events. So, why am I saying this? Because if you think about our systems, okay, you go to someone and you talk to them about the software, and they're like, why would this ever crash? It's like, aha, because you're going to run this thing at a rate of, let's say, 100,000 requests per second for 10 years. That's a lot of chances, a lot of times that this thing could fail. Eventually, it's going to fail. Everything that's real eventually will happen if you have a large enough system. And we do. But the thing is, it's actually more severe than that, because what we don't take into account is that there are many, many, many more options for those things to happen than we realize. So I'm going to give you an example. Most of you already know this. It's called the birthday paradox. And basically the question is this. If we go into a room and there's a bunch of people in the room, what are the chances that at least 2 of them share a birthday? So actually, if we think of, let's say, how many people need to be in the room for the chances of this happening being over 50%, okay? Just think of this for a second, come up with a number. I'm going to give you the answer in a bit. It's 23. Only 23 people need to be in a room for the chances of 2 people sharing birthday be over 50%. And if you look at this chart here, it goes over 90%, around 40-something, and around 50-something, it's like close to 100. So not a lot of people need to be in the room for the chances of a birthday collision to happen. Now, okay, now think about UUID. What are the chances of 2 UUIDs colliding? Much, 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 much higher than you would think. Okay? And why? This is why. The reason is that the number of interactions grow at a rate of n squared. Okay? But if you think about any subgroup, not necessarily pairs, but any subgroup, they grow at a rate of 2 to the power of n. That's like an insane number. Okay? It grows really, really fast. If you think about this physically, you could say that volumes, the internal volume, grows at a much higher rate than the surface. And this is actually a real problem for scalability in the physical world. For example, the reason mammals can grow too big is because we produce heat, and the heat has to come out through our skin, and the skin is basically the surface, and the volume scales much faster than the surface. Okay? So at a certain, basically certain size, you produce more heat than you can evaporate through your skin, your surface. Okay? So our systems are discrete, so we cannot talk about volume, but we can talk about interconnections. And the number of interconnections grows really, really fast. Okay? It scales much faster than the surface. In a sense, you could say that the interactions, or the subgroups, they scale superlinearly, where the surface scales linearly, in a sense. So now we can talk about emergent behavior. What is emergent behavior? Emergent behavior is basically behaviors that happen in the system, that emerge from the system when the system becomes large enough. And in a sense, it's when we switch models from having a model of particular objects and instead using a statistical model of the entire system. That's basically emergence. Philosophically, we could ask, when do grain of sand in this case become a heap? Or when do drops of water become rain? Okay, if you think about this, you don't get wet from drops of water. You get wet from the rain, right? No single drop of water will make you wet. And it's the same question about grains of sand and so on, so on, so on. So to illustrate this, we're going to play a game for a second. So I've put the instructions here. I'm going to read them, and then I'm going to play the game. So each one of you choose a number between 1 and 5. Let's call that number x. Okay? And then wait until you hear someone clapping their hands. And if you do, clap your hands x time, the number you chose, and then wait x seconds, and then do it again. Okay? Everyone got the rules? Everyone chose a number? Okay, don't clap unless you hear someone clapping. Okay. So first of all, I want to comment that someone cheated, because someone clapped before they heard the hand clapping. But notice what happened. Once someone started clapping, everyone started clapping. Okay? So now we're going to do this again, but in a slightly modified version. Okay? You, Emil, please clap your hands. Just clap. Okay. So you can see that there's no problem hearing me speak while he's clapping, right? Now everyone clap. Clap, clap, clap. So, okay, stop. This is the difference between noise, which is an emergent phenomena, and a person clapping. And actually, we could do this a number of times, like have one row clapping, and 2 rows clapping. And what you would notice is something very interesting. The switch between a small number of people clapping and noise is non-linear. Okay? It's not like the noise increases regularly until at some point you can't hear me. There's a point where suddenly you can't hear me speak anymore. And why is that? The reason is because words have a definite length. Okay? There are no words shorter than 1/10 of a second. Words have a certain minimal length, and this characteristic length at some point is, if you clap your hands and you have enough people clapping, at some point the gaps between hand claps will be small enough that no words will, statistically speaking, be able to fit between the claps. Okay? So, 1 second. So basically what I'm saying is that it's a statistical phenomena, and the switch is nonlinear as we observed. So where do we observe this in computers? So everybody's heard of remirroring storms and retry storms and so on. I'm going to explain this really quickly. I've also put a QR code. This links to the Amazon failure report from 2011, where they had a EBS remirroring storm. But basically what happened then was that they have a fleet of storage servers, and each server replicates to 2 other servers. And when one of those servers, the peers, the replica peers, fails, then the EBS server would pick another server to replicate to. And the initial replication takes time, because they have to replicate all the storage that they had until that point. And everything's fine as long as you have enough capacity. But once enough servers try to remirror at the same time, and they consume all available capacity, or they consume the network bandwidth, or whatever, then other servers would also fail because of the increased load, and would also try to remirror, and all of a sudden you have exactly the same phenomena that you saw here with the hand clapping. Okay? You have a storm of everyone doing the same. Okay? Same thing happens with retries. You have a server or a service, and everybody's, if you have a failure to connect to that server, you wait a while, you retry, which works fine until everyone is disconnected to the server, and suddenly 100 million clients retry at the same time, the server gets hammered, and you have this feedback loop going again and again and again. Okay? So this is a storm. We have a lot of storms in systems. People who worked at data centers know the spanning tree storm. Yeah, that was a bitch. So we have quite a lot of them. This is another example of emergent phenomena in computers, and this only happens at scale. Okay? Emergent phenomena in general only happen at scale because it's a statistical phenomena. So emergent behavior is something where we feel the aggregate impact. We don't feel the impact of every single occurrence. We feel the aggregate impact of all occurrences. And in that kind of system of behavior, the interactions of elements is what dominates. Okay? We switch to a model of emergent phenomena when the interaction between elements is what dominates as opposed to the individual effects. And the emergence is nonlinear. So this one, I'm going to talk about state, but a lot of you are going to say, like, state? But wait, my system is stateless. How can you be talking about state? And we all know it's bullshit, right? There's no such thing as a stateless system. Because even if you have a bunch of servers that are supposedly stateless, they are connected to form a system in various ways. So, for example, in this system, yeah, maybe the app servers are stateless, but they are connected through a load balancer on the front and also through a database on the back. Okay? And that connection between them is what forms the interaction between those servers. So those servers actually interact in various ways through the interconnections. Now, there's a lot of other connections that we don't see on this diagram. For example, the network. The network also connects those servers and also potentially is a place where interactions can happen. So we have a lot of implicit connections between parts. And if you remember from before, once you have interactions, the amount of interactions, it grows much faster than the number of parts. So in this kind of system, you only have 4 servers, but actually the number of possible interactions is very, very high. So even in a stateless system, we have what is known as emergence of state. Okay? The interactions themselves are state. So think about a system where the servers talk to each other on TCP, for example. TCP has state, right? It's in the kernel, it's in the routers, it's in the load balancers that the TCP connections go through. It's everywhere, but we don't think of this as state usually, unless we're network engineers or we do systems programming. But it is still state. The power in the data center, and I mean like the actual electrical power, is also state. And how do I know this? Try to reboot 10,000 servers at the same time and see what happens. This is how I know it's state. And the thing about this kind of state, it has super linear scaling, because for every TCP connection, you hold state at 2 points, not 1. Okay? So remember from before, the burst-wave paradox, it's basically the same. And the propagation time of this state increases with scale. Why? Because we have to update more and more peers. And this is what limits the scalability of many systems. If you think about blockchain, blockchain is not scalable. And why? Because it has to update half the planet whenever something happens. Okay? That's basically the problem. So the lesson here is very simple. All large systems are essentially stateful. And this has a lot of implications. First implication, what happens when you reboot a stateful system? Anyone? What? It loses its state, yes. Every stateful system is one of a kind. You cannot reboot a stateful system and have it resume at the same state. It's impossible. It will have a slightly different state. And this means that rebooting a large system is very problematic and very dangerous as well. Okay? And you can see this on every major outage where they try to recover, and the recovery is very, very hard because during the recovery, they discover a lot of problems that didn't exist before, or state is recovered in a slightly different way. It's no longer the same system in many ways. So, yeah, that's kind of a bummer, really. And now we can talk about the universal scalability law. So the universal scalability law is a model of scalability that was created by Dr. Neil Gunther quite some time ago, I think about 25 years ago, something like that. And it's a model which, of how things scale that can actually be used to predict the scalability of systems. You can do a load test and fit it on the universal scalability law and actually do some predictions. Now, this model, which I'm going to explain in a second, is what we call an optimistic model. It gives results which are slightly better than reality because it doesn't take everything into account, but that's fine. Why? Because all models are wrong, some are useful. It has to be good enough, no more. Okay? So what is this model? So the green line is perfect scaling, what we talked about linear scalability, and the blue line is Amdahl's scalability. So we all know Amdahl's law basically says that the speed up you get in a parallel system is limited by the serial part of execution. Okay? The universal scalability law goes one step beyond that and adds another type of interaction, which is consistency. So this is basically the formula. You don't need to remember the formula. But basically the idea is that it has two things that limit scalability. One is contention, alpha. This is a parameter for contention, which is basically the same as Amdahl, queuing for a shared resource, waiting for a shared resource, the serial part, if you will. And beta, which is consistency. It's coordination between processes. So just to give you an example of what is coordination between processes, if you know Zookeeper or Consul, on one of them, they have to have consensus between the masters. That consensus is coordination. Okay? And once you have coordination between processes, once you have a number of processes that need to reach to some unanimous decision or sync data between them, then they are going to wait for each other. And if you look at the formula, you would see that beta is basically a parameter for something that is n squared, okay, like interactions. Okay? So you're going to start seeing the impact of beta very, very fast. And that's basically what we need to understand. So contention, like I said, it's waiting for a shared resource. And usually it would be affected by queuing. Okay? So what is queuing? You wait in line. Okay, we all know what queuing is. We've experienced it in the bathrooms before. But we're going to talk about it in a little bit. And it's limited by shared resource. Okay? So everyone who's waiting is limited by one shared resource. Consistency, on the other hand, is coordination between processes. There's a lot of things where this happens. So I mentioned a few of them, like consensus, but there are many more. And basically, every time we need to somehow sync data between processes, we get a consistency penalty. And the thing about this is that the processes have to limit, they have to wait for each other, and this means that any process can limit this kind of behavior. Okay? So if you have n processes, it's enough that one of them is slower for the whole system to become slower. And that's really a problem. So what about latency? So this is, we can actually get from the universal scalability law the predicted latency of a system using another mathematical law that is known as Litter's law. And this is a plot of the latency of a system as it scales. So you can see that as we add more and more processes or as we add more nodes to the system, the latency, this is the average latency, becomes worse and worse and worse. Now, if you think about it from an SLA or an SLO perspective, you would realize that actually you can't scale this system, right? Because at some point, the latency would cross the SLO. So in many cases, the system becomes unscalable long before we get to the predicted maximum of the universal scalability law. So how do we scale things, knowing everything we know about the universal scalability law now? So we have a science fiction way of scaling things, which is warping space and time. Boo-hoo. What do I mean by this? So if you think about our data systems in two dimensions. One dimension is time. Okay, we have events of mutating data, reading from data, and they're on a timeline. And then we have space, which is basically the data we have, sorted or not sorted, but differentiated by some ID. In key-value systems, it's just a key. In other systems, it's maybe a primary key or whatever. You get the idea. Okay, so this is the two dimensions we have, space and time. So we can do a space warp, which is either sharding or replication, meaning we can segment our space into parts that don't connect to each other. Okay, they're completely walled off from each other, or we can copy the space. We can duplicate the space several times. Okay, and the idea is basically that we don't have interactions between the parts, so we have a smaller space, and each part of that space has its own USL curve. Okay, so that's one way we can scale. And the other way is we do a time warp. So again, we have two time warps. We have reordering, and we have lag, which is slowing down time. Okay? So reordering is basically like sharding, but for the time dimension. We basically say that there is no relation between events, and if there's no relation between events, we can do them parallel. We can just do them, in some arbitrary order that we want, and this enables us to do things in parallel and basically get to linear scalability. And lagging basically means that we slow relative time between parts, between workers. Okay, and again, this means less interaction between the parts. So if we put that back on the universal scalability law, this is what it looks like. If we have sharding and reordering, okay, that's the left side of the space and time warps, we have linear scalability. That's how we get linear scalability, basically. And if we have replication combined with the time warp lag, okay, we get diminishing returns. We get to the serial part, the Amdahl's law scalability. But if we have no warps and everything is synchronous, then we get retrograde scaling. Okay, so that's basically how we design our systems to scale. And now we're going to get to a Q theory crash course. So if you remember the parameter from the USL, this one, contention. So contention was queuing, basically. Okay, this parameter alpha, looked like a static parameter, but actually this parameter is impacted by queuing, so we can understand how this parameter behaves. So this is why we need a Q theory crash course. So what is a queue? A queue is just a space where incoming work, queues on, waits. And when we talk about latency, we actually talk about two things. We talk about the service time, the time it takes a worker to do the work, and the wait time, the time we wait in the queue. This is what latency is composed of. The interesting thing about service time is that service time is not constant. It's actually a distribution. Most of the time we talk about averages. We talk about average service time, or if we are more advanced, we talk about the percentiles of service time. But what we need to remember is the distribution. Okay? So what's the problem here? The problem here is that, let's say the service center now has to deal with some work item which is much, much longer. Everything in the queue has to wait. Okay? This is known as head-of-line blocking, and the queue will form up really quickly. But if, for some reason, the service center has finished up early and there's nothing in the queue, what happens? Time just goes to waste, right? You cannot bank spare time of the service center without work. You cannot bank it. You cannot save it to the future. So it's kind of a lose-lose situation. If, for some reason, you have a lot of things in the queue and the service center is delayed, or maybe, statistically speaking, you had a lot of work that came on at this minute, you lose. And if for some reason the service center finishes early, but there's nothing in the queue, you also lose. Okay? So that's why queues are formed, even when the utilization is relatively low. This is what it looks like on a chart. Okay? So this is a chart of latency or queue size versus the utilization. Okay? Utilization is basically the capacity of, the amount of work that is incoming divided by the capacity of the service. And it's between 0 and 1. Okay? And you can see that it rises non-linearly when you're nearing the utilization of your service. So once you get to around 70, 80%, start to rise really, really, really fast. This is a model for a very simple model for some known distributions. Not going to go into that. There are quite a few of them. And some of the models can take into account general distributions. But they all look kind of like this. Maybe like the behavior is the same. Maybe the parameters are a bit different. The takeaway here is that it's non-linear. It starts to rise really, really fast. Now, this has a lot of implications. I've done a few talks about queuing theory, which you can look online. Other people have done very good talks about this as well. And I think this is a must for every software engineer. But the point is that we have to run our system at reduced capacity. We have to run them underutilized. Otherwise, we would start seeing latency increase that's like basically an outage. Okay? But the thing is that if you remember from my explanation before, the reason why we have queuing is because of the statistical distribution, because of variation. And we can actually see this on the graph. So this is a slightly modified formula. This is known as the Kingman formula of queuing. And what is nice about this one is that this shows you the C's here are actually a measure of variance. So as the variance grows, our utilization curve becomes worse and worse and worse and worse and worse and worse. So when the variance is high enough, you can see that the latency will start to rise even at relatively low utilization. And in this kind of system, where variance is high, we won't be able to get even to 70% utilization before latency is too much. Okay? So what we need to understand is that we need to control variance in order for our systems to have decent latency. And if you remember, because the parameter alpha is related to queuing, this also means that the parameter alpha will be much higher when you have high variance and your system will become unscalable. Which brings me to talk about failures. So everyone knows tails at scale from Google, so this is fail at scale. So we have two types of statistical failures. One is a component failure, and the other is an interaction failure. And they slightly differ in their behavior. So component failure could be hardware failure, or maybe out of memory. It could be a kernel crashing. It could be any number of things that happen on individual servers or individual workers or individual nodes. Okay? And the interaction failure is, like the name says, a failure of interaction between two or more of those components. Sorry. Now, component failures are independent. Therefore, they have linear scaling. And dependent failures have superlinear scaling because it's enough for one of the participants in their interaction to cause some failure in order for you to have an interaction failure. But think about this for a second. If our system has sublinear or retrograde scaling, and the failures have linear scaling or superlinear scaling, just imagine what would happen to the error rate. Okay? So this is an extrapolation from the universal scalability law of component failure rates and interaction failure rates. Okay? Rate, remember, it's the number of failures divided by the throughput, basically. So you can see that the interaction failure rate rises very, very high, and the component failure rate also rises, although it's a slightly reduced speed. So what this means is that as you scale a system, you will start to see more and more errors. So you cannot just add more resources to a service and expect to have the same error rate. If you had, let's say, 1% error rate, it will become higher and higher as you scale. So this is something that has to be dealt with in order to scale. So statistical failures, okay, and of course, remember we had growing latency from the USL. Eventually, we will hit timeouts, so that's an added failure mode that will also happen. And if you have timeouts, you're going to have clients retrying, which causes more demand on the system. This is known as failure demand, which will also limit your scalability. So it's actually much worse than this. So we have reached the end of our talk, fortunately for all of you. Let's talk about how we scale. So first of all, first rule, lower the variance, raise the mean. You cannot grow a system, you cannot raise the mean of the system, be it latent, improve the latency of your system, improve the scalability or capacity of your system without lowering the variance first. This is like the first rule of scaling, lower the variance before you do anything else. Second thing, avoid coordination whenever possible. Even if you can't do this, okay, but especially if you can't do this, you will have to warp space and time, okay? If you don't know how, ask Captain Picard. Reduce statistical failures whenever possible. You will have to do this anyway because as you scale, statistical failures will have more and more impact on your system. Now, I didn't invent any of this. Those two guys invented most of those things I'm talking about, not Q-interior and that kind of stuff. But this is on the left, like here, my right, your left, is Walter Shewhart. And on the right, like your right, my left, is Edward Deming, William Edward Deming. Shewhart was a mathematician who worked at the early 20th century. Deming was a student who followed up. They invented something called statistical process control. And one of the things, maybe the one thing you need to remember from their teaching is that the key to scaling is quality. And they define quality as less rework or uniformity, meaning less variance. I highly recommend that you read Deming books or Shewhart if you can find them. There's a lot more to learn about this, so I'm just going to leave you with that. And like I said before, mathematics is really, really good for engineers and everyone else. It helps us think. It helps us reveal, the challenges, and the models help us reveal scaling challenges and challenges in general. Highly recommend that you get into math. It's not scary. It's not that complicated. And with that, I leave you to not lunch, coffee, I guess.